Hello, welcome to my channel. In this video, I'll be taking a deep dive into AMD's new RDNA2 graphics architecture and talking about some of the changes between it, RDNA1, and GCN. If I get anything wrong in this video, please leave a comment in the comment section below because this video took a ton of time to research and I definitely didn't get everything correct because I'm diving into some new territory with this video, learning many things that I hadn't known about before. So let's start with what is RDNA. RDNA is AMD's next generation graphics architecture. It is a full redesign of its predecessor GCN. Before we talk about the brand new RDNA2, however, we must talk about what came before it, which was RDNA1. The fundamental change between GCN and RDNA1 was the move to a SIMD32 dual compute unit that shares an instruction cache, L0 cache, and a new L1 cache that is shared across many CUs, or compute units. The instruction cache in GCN was shared between 4 compute units. With RDNA, each CU has basically double the instruction cache available to it. The large change in LDS between two CUs reduced traffic between the CUs, therefore reducing pressure on the global L2 cache as well as reducing power usage, as moving data around consumes more power than actually computing with it. The LDS also has dedicated ALUs that handle some data manipulation operations, both speeding up the data flow and freeing up the main ALUs from these tasks. The new improved LDS is a key in enabling the dual CUs to work together as a single larger workgroup, which improves performance in compute workloads. The new L1 cache is an array-wide shared cache that reduces bandwidth pressure on the L2 and also serves as a faster low latency cache for more commonly accessed data. With RDNA, SIMD16 was changed to a SIMD32 pipeline, and two of them combined with 2 scalar ALUs make up one RDNA compute unit, or CU. The ratio of scalar to vector pipelines per CU also changed from 1 to 4 in GCN to 1 to 2 in RDNA. As gaming graphics have become heavier on scalar operations, the effective gaming IPC, or instructions per clock, of an RDNA CU has greatly increased compared to GCN. The last major change between GCN and RDNA is the huge increase in registers available to each SIMD. GCN had 256 per, while RDNA quadruples that to 1024. According to my research, registers are extremely important when it comes to how much work a CU or SM is capable of doing concurrently. RDNA has also changed to a hardware scheduler to ensure better scaling with more shader engines and arrays, breaking through the GCN limitations and allowing RDNA to be used in much larger and more powerful cards. All of these changes resulted in AMD leapfrogging multi-generational gains from NVIDIA. NVIDIA's effective performance per CU or SM was so far in front by the time of Turing versus GCN, you could even compare it to the Intel Core versus AMD Bulldozer situation. Yet, similar to Zen, RDNA delivered an effective IPC gain similar to Zen, if not better. For the first time in a very long time, a single AMD GPU compute unit is on par with an NVIDIA streaming multiprocessor, or SM, in performance. In my opinion, this accomplishment is even more impressive than Zen, due to the limited amount of R&D funding that the AMD Radeon graphics division has to work with. Now that we've talked about what's new with RDNA compared to last generation GCN, this brings us to the moment we've all been waiting for: AMD competing with NVIDIA again in the high-end GPU market. Despite what many people were saying online, I stuck true to my belief that AMD would compete with NVIDIA's performance this generation, even at the top tier. And thankfully, I can say that I was right about this. AMD's new RX 6900 XT trades blows with NVIDIA's flagship RTX 3090, doing so at $500 less, or 65% of the cost. Early leaks and pictures of the die showed just a 256-bit bus for top RDNA2. This led many to speculate that RDNA2 had no chance of competing against Ampere, but oh boy were they wrong. Similar to what they've done with their Zen microarchitecture for CPUs, AMD introduced a new feature called Infinity Cache, similar to Zen's Infinity Fabric. People were wondering why the RDNA2 dies were so large despite being on the mature TSMC 7nm node, and this was because of their insane amount of cache. A RDNA2 compute unit is actually very small in terms of die space, while cache hasn't shrunken much over the past few years. AMD still managed to fit 128 megabytes of this new Infinity Cache on the die, however. This huge amount of cache is a similar approach to what they have done with their CPUs, allowing them to make up for latency by keeping important data in the cache close to the processing units. This Infinity Cache is what allows AMD to get away with using a 256-bit bus for even their highest end card. This overall reduces power consumption and allows them to put 16 gigabytes of GDDR6 on all of their high-end cards from the 6800 all the way up to the 6900 XT. Like I said in my previous RDNA2 versus Ampere speculation video, AMD will most likely tie or lose by a tiny amount in 4K, but this cache will let them dominate Ampere in 1440p and 1080p gaming. This paired with their new Ryzen 5000 CPUs, which boast the best single-threaded performance on the market, suddenly make AMD the best option across the board for high-end gaming. Taking all of these things into account, one thing is certain: now is a great time to be a gaming and tech enthusiast. Thanks for watching. The link to my website where you can find all other information about me is in the description below.